They are everywhere, marching across our kitchen counters, building tiny mounds of earth in our gardens. We often see them as simple, almost insignificant creatures. But if we look closer, truly observe, we discover something astonishing. The humble ant is part of a superorganism, a collective consciousness that achieves feats far beyond the ability of any single individual. These tiny insects build complex cities, they manage sophisticated farming systems, they wage organized warfare. They have been doing this for millions of years, perfecting strategies that we are only just beginning to understand. Their world is a miniature marvel of engineering, cooperation, relentless ingenuity, a testament to the power of working together. What is the secret to their incredible success? It is not the strength of one ant, but the unified power of the entire colony. Each ant is a small part of a much larger whole. It follows a simple set of rules, often without any awareness of the bigger picture. Yet when thousands or even millions of these simple actions combine, something extraordinary emerges. Communication is the invisible thread that weaves a colony together. But ants do not speak with voices as we do. Their conversations are written in a language of chemicals. This silent, scented dialogue is remarkably sophisticated. When an ant finds a source of food, it does not simply return to the nest. It leaves behind a trail of special chemicals called pheromones. This trail is like a signpost, a message left for its sisters to follow. It says, "This way, there is something wonderful to be found here." The strength of the trail can even indicate the quality of the food, allowing the colony to prioritize the best resources available. This chemical language is wonderfully versatile. A crushed ant releases an alarm pheromone. That alarm is a chemical scream that warns nestmates and calls them to arms. Other scents identify members of their own colony, distinguishing friend from foe. The queen produces special pheromones that regulate colony life. They suppress the reproductive abilities of other females. They maintain social order. The pheromones slowly evaporate, trails fade away, ensuring the colony adapts without wasting energy. The concept that emerges from this remarkable cooperation is known as swarm intelligence. It is a powerful idea, that complex intelligent behavior can arise from a group of simple individuals following simple rules. No single ant understands the grand architectural plan. No single ant has a map of the entire foraging territory. There is no leader giving orders. Instead, each ant operates on a limited set of local instructions. Follow the pheromone trail, pick up that grain of sand, attack that intruder. Consider the challenge of finding the shortest path to a food source. Ants solve this classic problem without any knowledge of geometry or mathematics. Those that happen to take the shorter route complete round trips more quickly and reinforce it more often. They reinforce the shorter path with pheromones more frequently than longer routes. Very quickly, the shorter path becomes a superhighway of scent. A simple, elegant solution derived from collective action. When building a nest, ants do not follow a blueprint. They follow local rules. Pick up a grain of sand. If you find a pile, drop it. From these basic commands, intricate tunnels and ventilation shafts emerge as if by magic. The same process lets termites build colossal, air-conditioned mounds. Decentralized control makes colonies resilient. If a group of ants is lost or destroyed, the colony barely registers the loss. This robustness is a key feature of swarm intelligence and hard to replicate in human-engineered systems. Inspired by the elegant efficiency of the anthill, scientists are now building their own robotic swarms. These are not the complex human-like robots of science fiction. They are often small, simple, and relatively inexpensive. Just like their natural counterparts, the power of these robotic swarms comes not from a single unit, but from their ability to work together. Each robot is programmed with simple, ant-like rules allowing them to cooperate without a central controller. The goal is to replicate emergent intelligence we see in nature. One direct application is pathfinding, mirroring how ants discover the shortest route to food. Imagine a disaster zone where groups of small robots are deployed to find survivors. Instead of being individually remote-controlled, they can operate using a swarm algorithm. As they explore, they leave a digital pheromone trail, a wireless signal, in their wake. A robot that finds a point of interest can strengthen its digital trail, guiding others to the location. This allows the swarm to quickly map a complex, unknown environment. This concept has been brought to life in labs around the world. At the Harvard Microrobotics Lab, researchers created swarms of over 1,000 kilobots. These tiny machines coordinate to form complex shapes purely by communicating with immediate neighbors. They have no leader and no global knowledge of the final pattern. They simply follow local cues like ants do, and a complex pattern emerges from those local interactions. They don't need powerful processors or complex sensors. Their strength is in numbers and interaction. The applications of ant-inspired robotics go far beyond the laboratory. Swarm intelligence offers practical solutions to some of our most challenging real-world problems. Logistics and manufacturing. Fleets of autonomous warehouse robots are already using these principles. Robots shuttle goods across vast fulfillment centers, coordinating to avoid collisions and find efficient routes. They respond dynamically to new orders without a central traffic controller. Environmental cleanup. Imagine thousands of small autonomous boats after an oil spill, each following simple rules. If you detect oil, move toward the highest concentration and release a cleaning agent. Emit a signal that attracts nearby robots. The swarm converges on the densest parts of the spill, cleaning faster than a few large ships. This idea is being explored for plastic cleanup and pollution monitoring. Agriculture. Swarms of small specialized robots could replace heavy tractors with teams of lightweight machines performing targeted tasks. One group planting, another weeding, a third applying microdoses, minimizing waste, improving yields. Medicine. Scientists are designing nanorobots injected into the bloodstream that navigate chemical gradients like ants use pheromones. They could seek targets with collective precision to destroy cancer or deliver drugs with minimal side effects. One of the most visually stunning examples of ant cooperation is their ability to build. Vast subterranean cities and living bridges formed by army ants, master architects. They achieve this without any master plan. Stigmergy. Individual actions change the environment and trigger follow-ups. That idea is now programmed into construction robots. Imagine robots building a wall on Mars, placing one brick next to another. Over time, a structure emerges from simple placements. This is being tested in labs. Robots stacking foam blocks, assembling trusses. Simple local rules produce planned designs, slowly but robustly and without complex oversight. The robots observe the environment and react. They don't always need direct communication. Exploration is another area for swarms. One expensive rover can fail. Hundreds of small rovers provide redundancy. Send many small rovers, they fan out, mark finds, and call others with digital pheromones. Rovers mark finds. The swarm assembles around samples and continues the mission despite failures. Scalability. Add more robots to build bigger structures and explore larger areas. Resilience. Losing units doesn't stop the mission. Parallel work. Many robots finish tasks far faster. Whether building habitats on other worlds or exploring deep ocean trenches, many tiny coordinated steps are best. Digital pheromone markers let robots call others to investigate important discoveries. The collective approach solves many problems and scales naturally. Swarms provide scalability, resilience, and parallelism, direct lessons from the anthill. For millions of years, nature has been running experiments. The ant colony is one of its most successful creations, a perfectly tuned system for survival and prosperity. By studying these tiny creatures, we are not simply copying them. We are learning fundamental principles: the power of decentralization, the elegance of simple rules, and the extraordinary potential of collective action. The anthill is a classroom. Its inhabitants are our teachers. They show us a different way of thinking about intelligence, not confined to a single mind but spread across a community. The future of robotics may look less like a single brilliant machine and more like a bustling cooperative colony. We envision swarms working in our fields, cleaning oceans, assembling products, and venturing into space. These machines will be adaptable, resilient, and more efficient than many technologies today. They will tackle problems at previously unimaginable scales. As we learn, we deepen our appreciation for the complexity and genius around us. This journey reminds us that sophisticated solutions can come from unexpected places. It fosters humility and wonder. We are still students of the natural world. The anthill is a tiny guide pointing us towards a smarter, more collaborative future. The ant, marching tirelessly across the pavement, is no longer just an insect. It is a symbol of cooperation, a marvel of emergent intelligence, and a tiny teacher for our technological future.